So where we stopped, I believe last week, was looking at our OSO4. When you see OSO4, you need to do a syn dihydroxylation reaction. So syn, we're adding to the same side of the pi bond. So they both need to be wedged or both dashed. Either is fine. And since it's a dihydroxylation, so di meaning two, hydroxylation meaning OHs. Okay. That's what you do when you see OSO4. Officially, you do need some other sequence of reagents. Peroxide is an option. I've seen HSO3 minus show up. I've seen water show up. Okay. I've seen enough variety of reagents there that I actually don't know what is necessary to cause it to happen. Okay? Because I've seen it on the final written as just OSO4, and I'm expecting you to put the dialcohol. Okay? So be aware of that. If you see OSO4, just immediately put on the two alcohols. What's the what?
I was more talking to myself, asked what does it react with water, and then thought about it because that's the only place where H's could be coming from.
It's got a sizable amount of stuff it's got to do. You have to satisfy that osmium. There are other reactions or reagents that will do the same thing. Potassium permanganate will do the same thing, right? Which you might look at and be like, well, that kind of makes sense. Why would we say that kind of makes sense? You look at potassium permanganate, that's KMnO4. The first thing you should do is convert that into MnO4 minus. Why are we immediately ignoring the potassium? Potassium is a group 1 metal, spectator ion. So MnO4, why might we expect MnO4 minus to act similarly to OSO4? Manganese, oh, that's a transition metal. Osmium happens to be a transition metal. Bound to 4 oxygens, bound to 4 oxygens. Guess what? It does effectively the same chemistry, okay? With some minor caveats that we'll have to watch out for in a second. So when we look at our conditions, when you see permanganate, you have to look at the conditions, okay? So one of the big things is cold and dilute, okay? Do we see temperature show up in our reaction equations? We look at an equation to say, oh, it's cold or it's hot. It's usually fairly rare. Sometimes you'll see it as a delta. Okay? The cold here is important enough that we'll actually specify cold. Sometimes you'll see temperatures written in, but they're usually really, really cold temperatures like minus 78. Okay? That typically is the only temperature that gets specified is minus 78 or lower. So the other conditions, cold, and you'll see hydroxide, so the presence of a base. Okay? So those are your big kind of conditionals for this. If those are present, then you get effectively the exact same mechanism-ish as the osmium tetroxide. It goes through, it does a syn dihydroxylation reaction, ta-da, done. Why would we pick one reagent over the other? The ish? Oh, I said same-ish, yeah. Partially that. Where's manganese on the periodic table relative to osmium? Above it. In general, what can we say about elements up at the top of the periodic table that we typically can't say about the elements at the bottom? More stable. It's an interesting concept. That's probably it's going to be part of it.
Smaller.
We can look at size. It's less important. If it's more stable, what does that mean? How many stable people do you see in the world? Well, that could be a really bad question. Okay. The higher up on our periodic table, typically the more often we see those elements. We get a higher abundance. Why is that important? Well, if we have a whole lot more of manganese, what does that mean about permanganate? It's cheaper. Right? So the permanganate reagent tends to be much more readily available, so it also tends to be a little bit cheaper. Okay? Why would we prefer osmium over the permanganate? Well, the permanganate requires that hydroxide. It requires that base solution. What if you have a functional group that is base sensitive? Well, that's a problem. Right? So we can look at some of the other kind of conditions of how those reagents function to potentially decide one over the other. Much more important in second semester and first semester, you just kind of have to accept it. Hey, we use it. Okay? Not too concerned about the mechanism, but it's the same idea as that we did with the osmium. So we'll real quickly show that. We've got the manganese, we've got our oxygens. Whoops. Double whoops. It can come out horribly done, and we can get kind of a coordination. Okay? That's what I was attempting to show for this one. What happens if we react with the alkyne, though? So if we go through and just, whoops, man, stop erasing. If we get rid of one of those pi bonds and replace it with an OH, whoops, and place them with both of them with an OH. Does that look familiar to anybody? Say if like I maybe color coded it slightly differently. Looks like an enol. We have the potential for a tautomerization to occur, and our alkynes will actually go through this process a little bit differently, and we end up with, whoops, the dicarbonyl. Okay? So it'll convert both pi bonds across to carbonyls. And since I don't have the, whoops, man. Stop counting whoopses. Get our diketone. Okay, so our alkynes can do some kind of interesting chemistry when we go through and react these. Okay, so our permanganate, well, then we just kind of jump ahead. We can then move to what's known as our oxidative cleavage. So what's happening is we're taking our alkene or our triple bond, or alkyne, and we cleave it completely through the middle, and we replace all of the bonds that were previously there with oxygen bonds. Right? So if we look at the alkene, let's call this a red carbon. Let's call this our purple carbon. The result is that when we cleave, we just cleave that bond entirely separate from each other at that position, and we'd end up with 2 bonds to oxygens. Okay? Because we started with 2 pi bonds, or 2 bonds, we have to end with 2 bonds to each of those carbons. And what we're doing is fully replacing them with oxygens. Same thing is happening with our alkyne, though a little bit less artfully shown down below. We have to replace all 3 of those bonds with bonds to oxygen. Potentially. If we replace all 3 of those bonds to oxygen, what product do we end up with? As a hint, it's not shown. Just take a look at the red carbon. Red carbon, we have 1, 2, 3 bonds. Those 3 bonds need to be at oxygen. So there's 1 and 2. I need a 3rd bond to oxygen. Where's the 3rd bond? It just wasn't shown. Put in a 3rd bond to oxygen. What functional group do we now have? Yes, Joey?
Carboxyl.
We have a carboxyl, technically a carboxylate if we're under basic conditions. If we're under acidic conditions, what would we have? A carboxylic acid. Okay. So the alkyne doing these oxidative cleavages is going to do effectively the same thing. We completely split the connection between the carbons and we replace those bonds with oxygens. That's it. Okay? There's a variety of reagents that allow us to do that. Okay? KMNO4, anybody have a problem already? What's the issue? Did KMNO4 split? Look at the previous slide. No, it didn't. And yet the very first reagent on our list of things that we need to know does oxidative cleavage is KMNO4. Well, that's a bit annoying, so we'll come back to that one. In big bold letters, IO4 minus, or periodate. Periodate will do this, but it will only do it if we're reacting with a diol. But doesn't this show alkenes? Yeah, so how do I get a diol from an alkene? KMNO4, or osmium tetroxide. So when we're seeing periodate, it is always a second. Got an alert, I need to buy new AC filters. The periodate will only react with the diol, not with our alkene. So we have to convert the alkene across to our diol. The other option is something like ozone. Okay, so there's two primary ones that we need to worry about. If you want to look at the periodate, the note there for the textbook is because it's in the textbook. You can check it out, look at it if you would like, but that is your call. Okay? The permanganate and the ozone are big ones that we need to worry about, so we'll take a closer look at those. When we take a look at permanganate, what happens? Okay? Well, we said what the final answer would be. We need to break that pi bond. So let's come up with our cheat before we look at a mechanism. Let's come up with a cheat so that we can get to the answer and say that's the final structure. Okay, well, the whole point of this is that we break the pi bond. So what I'm going to do is draw the pi bond again, but I'm going to stretch it out. Okay. The only thing reacting is the pi bond, so what happened to the rest of the atoms? They're the same. So I'm going to draw the rest of the atoms on. Okay, now here's where the cheat comes in handy. I break the alkene. What needs to replace the alkene? Guess what I've now drawn? The product. I'm done. That's the answer. Why does this then become problematic? Well, is that a particularly nice way to draw the structure? No. More than likely, what are they going to expect? Drawn out in a nice straight line. So or a zigzag, depending on what you're looking at. You'd have to go through, typically a good idea to count. 1, 2, 3, 4, 5. 2, 3, 4, 5. Position 1, I had a pi bond. Position 2, I had a pi bond. We now have a clean format that would show up in a multiple choice answer. Make sense? Okay. It can be made more complicated because I could add a carbon. Oh my God, now everything's different. No, I stretched the pi bond, I broke it. If I've numbered everything, 2, 3, 4, 5, I know at position 5, I have to draw a methyl. Make sense? Do we need to worry about stereochemistry? Wedges and dashes. Why not?
There's no stereocenters.
There's no stereocenters. So this is one of the nice reactions, kind of saving for the end of the semester. Yeah, it's a whole bunch of reactions, but we don't have to stress as much because we don't have any stereocenters. Okay? So that can make life a little bit easier to worry about. Okay? So mechanistically, what's happening in our process? That'll all get deleted here in a second anyway, but our pi bond tacks out, shuttles electrons, connects up. We end up with our 5-member transition state, okay, just like we did with the osmium. And now what can go through and happen? We somehow get cleavage. Okay. How is that cleavage going to happen? write that a little bit clearer, maybe you can see. Just for that. It's going to be a hard one for you guys.
Cares? Why care?
Who cares?
Play the hangman.
Pretty darn close to who cares, and we jump all the way to the final product of that. Okay? Where it's doing the final cleave all the way through, and we're happy with it. Okay? It's a bit of an overstatement. Okay? We want to go through and take a look at that final product. Okay? Is there some reactivity behind that new functional group? That's a hard question because it's a functional group that we haven't talked about. What is the functional group? Okay, it's the aldehyde. What is reactive of the aldehyde? Okay, I heard the oxygen and the double bond. Oxygen, I'm a little bit okay with. The double bond needs a clarification.
Pi bond.
The pi bond, yes. What is the pi bond doing? Being pulled to the electronegative oxygen, making the carbon very positive. What does this functional group introduce? A really good electrophile. We don't have as good of a nucleophile because, well, oxygen's already sharing its electrons. Okay? So oxygen's less likely to share those electrons outwards. Okay, but I do have a decent electrophile. What does that mean can happen? Well, under either acidic or basic conditions, okay, drawn in basic conditions, what do I have down there? OH minus. And OH minus is a nucleophile that could potentially attack. The result is we end up oscillating through something known as your carbonyl, hemiacetal, and acetal. That chemistry is super, super important and is one that is fully addressed and discussed in second semester. But it is also the reason why this reaction is working. Okay? The other reason why that's important for those of you moving into any kind of biomedical situations, carbohydrates, there are other people. Carbohydrates, all cyclize. If you've looked at a carbohydrate, they have that cyclic structure to them. If you look at that cyclic structure, they are hemiacetals. Right? If you look at the immune response in the body, that kind of goes to Brian Nolan for sure, for your biomedical engineering aspects. Okay? Carbohydrate immune response, it's coming from acetals. Okay? Understanding acetal chemistry is an important aspect of OChem, which is why it shows up in second semester. It's one of the reasons why this reaction runs the way it does. The instant that now concentrated base reacts, or even a concentrated acid reacts, is that I now form this new functional group. This new functional group I would call a what? What is that functional group? If I just look at one of them. An alcohol. If I look at the other one, it's a alcohol. What do I have? A dialcohol or a diol. What happens when we have diols? Your permanganate can react. Your permanganate can react again, form another cyclic structure. Why is that important? Well, then what happens? If it can coordinate, it can oxidize again, which then means I don't end at an aldehyde, I'd end at to oxidize means I have to increase the bonds to oxygen. What functional group do I end up with if I increase the bonds to oxygen on carbon? That is a carbonyl, guys. That has 2 bonds to oxygen. I want more bonds to oxygen than are what currently shown. I could show a triple bond to oxygen. That's not a super common species, but it does pop up. It certainly won't pop up when you're attached to another carbonyl. So if I need another bond to oxygen and it can't be the same oxygen,
Another alcohol, an H.
add another alcohol. Okay, I'll kind of accept another alcohol. So what would that look like?
There you go.
L-carboxylic acid. So recognizing our oxidation stages along the way can be helpful. Okay? We can stop at the aldehyde. The issue is that permanganate is super reactive. Once it initiates, it's going to cascade all the way down to the carboxylic acid. It will fully oxidize. Okay? So,
Why doesn't that happen on the other side?
why does it not happen on the other side? Who said I was done? What now happens to the structure? It happens again because I still have a reactive aldehyde. That reactive aldehyde can go through the whole process again. And what I end up with is not the dialdehyde, but the diacid. Both positions oxidize. Okay? So permanganate is an insanely fast or insanely strong oxidizer, and it will oxidize all the way down. So how did we get it to stop before?
Add water. Stop adding manganate.
One option was that I stop adding permanganate. Wow, it's way back there. So instead of using concentrated permanganate, I used dilute permanganate. So if I limit the concentration of the permanganate, I get less oxidation. Well, that makes sense. There's less species there to do the oxidation. Okay. What else did I do to limit the oxidation? I diluted it. Okay. That's less. That goes back to the concentration. Temperature. How active do you become if it becomes sub-freezing?
Not very active.
Okay? If we drop the temperature enough, we can limit the activity of the chemicals and they don't react as much. So if you're looking at cold permanganate, you're usually stopping the reaction relatively quickly. You're doing just the diol. The instant you up the temperature, concentrated and hot, both of those conditions perpetuate, and we end up doing, number one, the full oxidation down to our carbonyls, the whole oxidative cleavage, but those functional groups can continue to react under those hot conditions, and we can get all the way down to our diacid, which, as Joey was trying to list it out, I was fishing for, because I don't actually have that answer shown. But guess what the answer to question number 1 is in the predicting the products? So with that, since no one seemed to catch that, I'll let that slide. We've got a couple things popping up. Number 1, it says step 1 and step 2. That means there are 2 distinct steps. These are not all happening at the same time. You need to finish step 1 before you even evaluate step 2. So some people are like, well, why is there HCl? Okay. There is a very important reason why that we have to show HCl. If we don't show it, then the reaction doesn't get us to our final product or a stable final product. If we go through and use our permanganate, the first thing that would happen is we'd form our dialdehyde. But then what do we have to recognize? We still have that electronegative carbon. We still have that nucleophilic oxygen. What happens?
So the HCl is preventing the OH from attacking.
I haven't even talked about HCl yet. You form the diol. What happens when we have the diol? Permanganate coordinates again. And what happens? 1, 2, 3, 4, 5.
Does that bond go into a high?
I would get my OH. I would get the carboxylic acid. What's the issue with the carboxylic acid? I'm in what environment, Joey? a basic environment, which means what would happen immediately to that hydrogen? It's gone, and I'd be left with O minus. That was only on that rightmost carbon. What about the leftmost carbon? Same thing. 1, 2, 3, 4. Oh, that is right. But now what happens? Hydrogen's removed. Okay, I'm in a basic environment. I've now done as much as permanganate can possibly do. Permanganate can't act anymore. Because it can't act anymore, I'm now done. The problem is that I have a negatively charged structure, and that's not a good place to end any reaction. So what do?
HCl.
We do step 2. And step 2 does what?
Coordinates the
Adds HCl, which adds
protons.
protons, hydrogens. What can those proton hydrogens do?
Satisfy the negative charge.
Satisfy the negative charge on our oxygens,
So it can do it for both?
and it'll do it to both sides.
Okay.
Even
That's
though
what we were
only have
wondering because there was only one.
It's not, it doesn't say concentrate HCl, so, you know what I'm saying.
I do understand what you're saying, and unfortunately that becomes an implied. There's an implied amount of HCl that's enough to satisfy that.
So it's always like that?
Yes.
Okay.
So is permanganate similar to Jones reagent, like where you need a hydrogen to start the oxidation process, or?
So there's an interesting couple questions in there. Number one, is it similar to the Jones reagent? Okay, for those of us not in the lab, what was the Jones reagent?
Something that's really toxic. Yeah, something you don't want to put a lot of test to.
Jones reagent was chromic acid, which is CrO4. Is permanganate similar to chromate?
Yeah.
Yes. They're both a metal, transition metal with 4 oxygens. They do act very similarly. In fact, given the proper conditions, guess what chromate can do?
The same thing?
The exact same thing. It can also react with alkenes. Okay? Not easily. Okay? Permanganate does it better.
It does it better.
So with the aldehyde, that
So-
hydrogen initiates the oxidation process. And
What you were then referencing after you said your Jones reference was that when you did the Jones reagent, you said, well, when we did the oxidation, we had to have a hydrogen. Didn't we talk about that in class when we looked at our definitions for oxidation and reduction? And to oxidize something, we had to increase the bonds to oxygen while at the exact same time decreasing bonds to hydrogen. It was a requirement. When we go through and look at our first starting intermediate after our first oxidation, do we have hydrogens off of our aldehyde? Yeah. What happens when we move down to our final product? What happened to those hydrogens? They were removed so that I could do the oxidation. Did I remove any of the carbons? No. Okay. So do I have to have those hydrogens? Yes, absolutely. Which is a really important question to ask when we're trying to answer the next question. Because when we look at the next question, what do we have? Fine, don't erase everything. We do our initial oxidation by stretching that double bond. And we then have to decide, can I oxidize these further? To oxidize further, what do I need to have? Whoops. I need to have a hydrogen at the position where the carbonyl is located. Right? Let's call it the red carbonyl versus the purple carbonyl. Does the red carbonyl have a hydrogen at that position?
Yeah.
No. It has a carbon, which then means can oxidize it. What about the purple one? There's an implied hydrogen there that you have to be aware of, which then means that one can be oxidized further. The answer we get at the end, 1, 2, 3, 4, 5, 6. Six carbons. I've got a methyl with our carbonyl, and then I have the carboxylic acid at the other end. Yes?
So by adding that alcohol, did we increase the bonds to oxygen and hydrogen?
evaluate the carbon where the chemistry happened.
Right. Oh, well, there was a hydrogen there. Now-
There was a hydrogen, so it lost a hydrogen where the chemistry happened, and it increased the bonds to oxygen. Did I add an extra hydrogen to the structure? Yes, but if we're really going to make that argument, you also then added 2 oxygen bonds. What's your net? Still adding more oxygen. Okay? Kind of makes sense? Unfortunately, that's all the best we can hope for. It kind of makes sense. That's all we really need out of this. Okay? Permanganate under concentrated conditions will oxidize the crap out, do oxidative cleavage, and split open your structure. Okay? What if you had a triple bond? So we did a quick, oh, this one's not quick. Thought it was quick because I had a couple other things going on there. So let's take a look at the first one. How many pi bonds do we have that can react? Just one. Why just one? The aromatic ring does resonance, which means those are not alkenes. Those are less than alkenes, which sounds kind of negative, okay? But they're less than alkenes and at the same time more. Those aren't reactive, okay? And so will not react to the permanganate. At this stage in the game, aromatic rings do not react. Done. Okay? What happens when we have that extra pi bond on the outside? Well, we can go ahead and stretch it. We have our benzene ring that went out. We stretch that out to a carbonyl. That other one we can stretch out to a carbon as well, which has 2 hydrogens attached to it. What do we get as products? Is that the final answer? No, why not? I still have hydrogens. So on the leftmost structure, what can I do? Turn it into an OH. Cool. And I'd have my benzene or my benzoic acid. On the rightmost structure, what would I have? Hearing that? Why another one? I have another H. So that's my final answer?
Yeah.
No.
No, why not?
I don't know.
Maybe it'll help if we write it in this format? Yeah? How does that help, Wyatt? What's that? Not formal charge. It's carbonic acid, and carbonic acid
It's very acid-like.
very unstable, very acid-like. Nice. Immediately decomposes into CO2 and water. What's that? That's exactly what goes on in the body. That's how we respire, is through carbonic acid. Yes. Okay. Exactly right. Okay? So that's what ends up happening. We oxidize that out. Because we had those hydrogens to do, we will fully oxidize that last carbon. What as fully oxidized as we can get is CO2. There is nothing further than that. Okay? What happens with the rightmost structure?
Will I have to?
What's that?
Can't you run the reaction with CO2 on plasma?
We don't want to worry about that right now.
It's not aromatic, so they all react.
They all react. Oh, dang it. I keep not seeing that. Fudge. Yep. Way to go, Mike. Make it more complicated. They all react. So which one do you want to look at first?
Start with the water.
What's that? The alkyne. So we cleave that. We have piece 1 and piece 2, right? What does piece 1 become? What's that? And another O. Why another O? We need 3 bonds.
Implied hydrogen.
There's the implied hydrogen. It's going to do the exact same thing, and yes, piece 1 is CO2.
Nice.
What happened in piece 2? We'd form the carboxyl. Did I miss carbon? No, I didn't. Now what happens? And break what? Could break both of those pi bonds. Will have to break because they're not conjugated with each other. And we could go through and break each of them individually. I would make the argument it's a little bit easier to break them both at the exact same time. Draw in some H's. Might as well. Thank you, Wyatt. That's what I actually wanted to hear. What was that?
You might as well draw O's instead of H's.
I might as well just draw them as the OHs, which is what they're going to become because we're under acidic conditions. Okay. And what I believe I heard Nolan say, but what about the steps? Thankfully, we don't care. Not about your statement, but that we don't care about the steps. Okay? So it's a question of finding those pieces. Why does this then become important? Well, the question could just ask, instead of what is the product, how many products? And in this case, we end up with how many products? We have 3. Okay? Or water typically doesn't get counted. Okay? They could show a list of structures and say which of these structures is a possible product. You'd have to go through and mark out all the ones that are possible products based off of that oxidative cleavage. Make sense? Okay. So that's what's happening when we're looking at oxidative cleavage. We have to break, see what's happening. Go for it.
Can you go through the alkyne again? I was kind of confused where you got that extra oxygen.
So if we go back to the alkyne, we'll go through and color it in blue. We have that blue carbon. How many bonds are shown to that carbon right now?
3.
3, which means there's an implied hydrogen. Right, so if we look at that, I have to, when I do the oxidative cleavage, each one of those bonds in that triple bond needs to be replaced with an oxygen bond. So there's 1. There's 2. Okay, and then 3 technically because of that pi bond, and then I have the H. Well, what can I do with the H? That could be turned into an OH, but then what I have formed, carbonic acid, and carbonic acid immediately turns into CO2 and water. There's where my oxygens are coming from. Okay. So when we cleave through, just like with the alkene, every bond of the alkene was turned into a bond to oxygen. When I move to a triple bond, guess what? Every bond of the triple bond needs to be turned into a bond to an oxygen. The specifics on where that oxygen is coming from would be looking at the mechanism. We don't need to know that detail. If you would like to know that detail, talk to me after class. And we can work through the detail of that mechanism.
So there's 3 bonds, but you have 4 oxygens.
Why do we have 4 bonds to oxygen now?
Or not, I said like you make 1, 2, 3, 4.
Oh, we're talking about all of where all of those oxygens came from?
Where the alkene was. Like, why do you have a
So the
carbonic
alkene was here, and we had an alkyne here.
Right, an alkyne there. I'm talking about the carboxylic acid. Like, why do I... Why
That acid? Or that acid? Or that acid?
Oh, sorry. The one formed after the alkyne, yeah.
Okay. Where did that oxygen come from? It was still part of a triple bond. Which then means we need 3 bonds to oxygen. The specifics of where the oxygen came from is your mechanistic step. That's looking at the permanganate and the hydroxide and the water. All of that comes into that mechanistic step. Okay? That is a detail that you don't need to know and is not worth spending time on or any more time on in class now. So talk to me after class when you look through it in more detail. Okay? The next one is our ozone. Ozone is O3. If we take a look at O3, we already saw some of its Lewis structure characteristics before. We have a pi bond between two oxygens, and then we have a single bond between two charged oxygens. Okay? The oxygen with the pi bond ends up being the most reactive as an electrophile, and the whole cascade starts with the alkene attacking. That breaks our pi bond to satisfy the positive charge. We then have electrons close enough that can immediately stabilize, forming positive charge on our alkene. This forms our first intermediate, which, if you want to refer to it, is I'm not going to say that. Maybe I should try. Malozanide. There we go, malozanide. It's a malozanide, okay, referring to the 3 carbons all connected to each other in the ozone formation, coordinated to the pi bond. Okay? What is the stereochemistry of that going to be? So, for instance, could I show one wedged and the other dashed? No. What would I need to show? Both dashed or both wedged. So the stereochemistry isn't bad. They just need to be on the same side. Okay? Then what happens? A whole crap fest of fun happens. You get a cycloelimination. You get what's known as a 4+2 cycloaddition because of the ring structures that are happening. All these fancy fun arrows, which, believe it or not, I think is very, very cool. Okay? I also think it is a waste of time to talk about it because you're never tested at that level. Okay? So what happens is you end at the end with your carbonyls. The exact same thing as what happened with permanganate. There's one added benefit that ozone gets us. Take a look at that final product for me and tell me, is that a product that I could get from the permanganate oxidation? There's an implied hydrogen there. What would the permanganate reaction do to that implied hydrogen? Oxidize it down to the OH. Interestingly enough, ozone has the ability to not do that. Okay? But it is a conditional ability. It is conditional on this extra step. This is technically a step 2. We're adding a different species. When ozone reacts with an alkene, it ends up at the ozonide. Okay, still a goofy 5-membered ring with 3 oxygens in it. That structure is still exceptionally reactive. Okay, and depending on what we do next with that structure, it either fully oxidizes or it stalls at the reduced or the partially oxidized state at the aldehyde. Okay? That process, DMS, is a pretty big key player. Okay? DMS for dimethyl. How do you name a CH3? Thank you. How do you name 2 CH3s? How do we name a sulfur? You got it right. Dimethyl sulfide. Dimethyl sulfide brings in that sulfur. Sulfur is a weird, goofy molecule that does some kind of bizarre stuff. Okay? One of its bizarre things that it will do here is it will grab oxygen. If it grabs the oxygen, can I do the final oxidation? Did you walk into a wall? It will grab the oxygen, preventing the last oxidative step. So when we go through and look at our final product, we might say, well, I'm missing that 3rd oxygen. Where did that 3rd oxygen go? Okay, we'll look at the other piece. There's our 3rd oxygen. DMS picks that up. Okay? To form DMS Oh, really creative. Where it is now dimethyl sulf oxide. Okay? Also known as a pretty decent solvent. Okay? That was actually considered for liquid injections. Needleless injections for a while. Never tried it, but I've been told that what you can do is take whatever substance you want, dissolve it in DMSO, and then just put it on your skin. It goes right through the blood or the skin layer. Yeah, it's kind of neat. I really wish I've tried it. The reason they didn't do it is because DMSO is actually kind of toxic. So.
Wait, why did they do it?
I almost bet that someone was just playing around in the lab and splashed some DMSO that happened, from what I understand, they were working with mint or mint extract, and they'd gotten some mint extract in the DMSO, and someone splashed some of it probably on their skin by accident and went, why do I taste mint? And that's probably where it came from.
Did he be care about it?
Yeah. So, ozone has an extra step, and if we control that step, we can change the oxidation that we run through. Okay? So the step 1, we have to add ozone through. That's the formation of our ozonide. Okay? Step 2 is the official cleavage. We either do it as a reductive cleavage, that means DMS. Okay? Which is kind of a weird thing to say. We're doing a reductive oxidation. What? But that's exactly what's happening. We're doing an oxidation reaction, we just aren't letting the oxidation reaction go as far as it possibly could. Right? That's why we call it reductive conditions. You are still oxidizing. Okay? Or you can follow under oxidative conditions. Okay? In the reductive conditions, how many oxygens do you see? 0. In the oxidative conditions, how many oxygens do you see? 2. How do you know it's oxidative? You see oxygen. How do you know it's reductive? You don't see oxygen. It's going to be the easiest way to try and remember that. Okay? What happens if you're under the oxidative conditions? Well, we'd still form the aldehyde structure, but now it can be oxidized. Okay? And the final product ends up being the carboxylic acid. Okay? So permanganate is useful as a full-on oxidizer if I wanted to oxidize all the way down. If I don't want to oxidize all the way down, that's when I bring in ozone. Kind of make sense? So ozone is kind of our caveat piece. Our, let's not go quite that far. Okay? That's the part that you need to remember.
Do you care where the third oxygen in the ozonide goes?
No. Oh, in the DMS conditions, I already told you, it went to the DMSO. Okay? When we're doing our oxidative conditions, that's our carboxylic acid. Okay? You also don't care. But, okay? Questions on that? Okay. Because we talked about oxidation, we also have reduction. Okay? Most of our reductions involve, in fact, I think all of our reductions involve fancy catalysts. Okay? And that's because to do a reduction, we have to increase the bonds to hydrogen. Well, really the only place that we can get hydrogen from is going to be elemental hydrogen. And the problem that we're going to encounter with elemental hydrogen, it's a gas. We can kind of go with not reactive. Why is it hard to get hydrogen to react? One of them has to react as a positive, one of them has to react as a negative. See positive hydrogens everywhere. Why is that a problem? It's not. What's the problem? It's the hydride. It's the negative hydrogen. Not stable. Okay? So we need something to stabilize, to act as an intermediary to facilitate these reactions. We take it a step further. Hydrogen is the smallest element. Guess what H2 is? The smallest molecule. I'm trying to get the smallest molecule to react with an alkene or anything. Okay? The interatom distance in an alkene is significantly larger than the hydrogen molecule. How do I get the hydrogen atoms to go to the individual carbons? Okay? We have kind of a size differential. Br2 was fine. Br2 could react really easily because Br2 was larger. It could sit and react with both. Okay? H2 being super, super small, we need something to catalyze that. That's where we bring in our metals. So you'll see platinum and palladium as your big common one. You'll see H2 written with platinum and palladium. Okay? Sometimes you'll see nickel pop up. They might call it rainy nickel. Okay? It's just another metal catalyst. Don't stress about the name. You'll hear Lindlar's catalyst, which we'll talk about. And then we'll encounter the last one. Okay? The last one stands out. Why does the last one stand out? Do you see H2? No. Do you see H minus? No. Okay, well, where are we getting hydrogen from to be able to do that? We don't have H2 or H minus. What else is weird about it?
The solid sodium.
Solid sodium. Sodium, always a spectator ion, and we never worry about sodium ion. Is solid sodium sodium ion? No, it is sodium metal. Sodium metal has that extra electron. What can that extra electron be used to do? Change the chemistry of our carbons so that we can add H+. Where do we get the H+ from? NH3. We'll steal it from the solvent. Okay? That one is our massive outlier. All the other ones require a standard surface metal catalyst, and what you're seeing is what's in the images shown. You have your metal catalyst. Hydrogen gas can coordinate to the metal surface. Your alkene can coordinate to the metal surface via the pi bond. The hydrogen and the alkene can get close enough to each other that an electron transfer can be facilitated between the metal, okay, and our substrates to attach hydrogen to one end of our structure. Okay? We can then attach another hydrogen to the other end of the structure. That process happens so fast that it prevents a very critical thing from happening. What is that very critical thing? Rotation, but a pi bond can't rotate. Sorry, I was being a jerk. You're right. During the process of the reaction, what happens to the pi bond? It breaks, which then means theoretically we could rotate. The process of this reaction prevents the rotation. Okay? When we form just that sigma bond, we still cannot do the rotation, which then means when I go through to look at the product, where are the hydrogens placed? On the same side of the pi bond, and I get a syn addition. Okay? And all of the H2 catalysts, every single one of them will add hydrogen to the same side of the pi bond. When do we need to worry about addition of hydrogen on the same side? If you have stereocenters in your product. If you don't have stereocenters, then don't worry about it. Okay? What happens if we have an alkyne? Same thing, except more. Should do it twice. Okay? Because, well, there's 2 pi bonds. Okay? So I can do it twice. Okay? What if I only want to do it once? What's that? We can try to attempt to limit the hydrogen. The hydrogen isn't the limiting factor, though. It's the hydrogen that's absorbed to the platinum that's the limiting factor. We can't control that. Or at least we can't control it by changing the hydrogen concentration. What we will try to do is limit how the alkene can react with the platinum catalyst. If we can prevent the alkene from getting to the catalyst, then we can't do the reduction. Okay? That's where Lindlar's catalyst comes into play. Okay? And for that matter, the sodium and the ammonia. Okay? Lindlar's catalyst is still a platinum and palladium surface, but that platinum and palladium surface is embedded with stuff. That stuff gets in the way that prevents the alkene from attaching. Which then means what happens? Well, the alkene never coordinates, which then means the alkene is never reduced. The result of using H2 then on an alkene, or H2 and Lindlar's catalyst on an alkene is nothing. Nothing happens. But if I add an alkyne, I can reduce the alkyne down to the alkene. The hydrogens will still get added in the exact same fashion as with H2 and any other metal catalyst. Okay? They get added on the same side, which then means the alkene that is produced using H2 and Lindlar's will be a cis alkene. Okay? We don't get the trans. Okay? What if I want the trans? Well, you can't use Lindlar's catalyst then. Okay? And that is now a super common question on the ACS. When do certain reagents work and others not? Right? How can I get the trans alkene? That's when I have to use the sodium metal. Okay? Why does that allow for the transformation? Because in the formation of the pi bond, I generate intermediates that allow for the methyl groups to go to opposite sides. Okay? In the case of the Lindlar's catalyst, the alkyne coordinates the platinum surface. It adds hydrogens exactly where the pi bond's located. It can't do any kind of change in conversion. The methyl or our alkyl groups are always aimed to the same side. Okay? So our big summary that shows them all, okay? That's got all of our reactions on it. When we're looking at our alkenes, we tend to care a little bit less about the stereochemistry. Trying to stealthily take pictures?
No, I was taking a picture.
Take it out of the slide.
I did.
That's what I just said too.
We only have to worry about it if we have stereo centers. People are weird. When we move down to the alkyne, that's where chemistry becomes a little bit more interesting. We've got our H2 and platinum and palladium and our rainy nickels. The same things that we had with our alkenes will fully reduce down. They will fully reduce again doing syn addition. That keeps your R groups located on the same side. Right? If we go through and do Lindlar's catalyst and then sodium or sodium metal, we'll get, again, stopping at the alkene, but depending on whether we want the cis or the trans product, that's going to determine the reagent we're using. Okay? And again, unfortunately, memorization is the best option here. Okay? Sodium metal acting as a reducing agent, I think, is a neat reaction, so we'll show it really, really, really quickly here. What makes sodium metal reactive? What does sodium metal want to become? A cation. To become a cation, what does it need to do? It needs to lose electrons. Why is sodium metal reactive? It has an electron. What can happen? Sodium metal will dump an electron into the alkyne. That now exceeds the electron capacity for the pi bond. The pi bond breaks. We end up forming a lone pair on one carbon and a negative charge on the other. We then have a negatively charged carbon. Does carbon want to be negatively charged? What is it going to do? React with something positive as quickly as it possibly can. Yes, it could react with the now positive sodium, but then we'd have an ionic bond and the carbon would still be negatively charged. So it needs to find something positive somewhere else in solution. Where's that positive? In our NH3. The electrons can come out, react. We end up forming a negative nitrogen. Is negative nitrogen a good thing? No. So why am I allowed to form it? I think I heard you saying it. Maybe not. Nitrogen can stabilize the negative charge better than the carbon. So nitrogen may be a horrible place to dump negative charge. That's why it's a bad leaving group. But it's a hell of a lot better of a place to dump negative charge than a carbon. Now what happens? I'll get my laugh when you turn in your exam. It's okay. We still have the radical. We still have the radical. More sodium can come in and react with that radical to form another anion. That anion can then pick up another hydrogen, and we'd end up with our final product. The hope there was not to intimidate you, but really to actually make you pay attention. So we get our big, long mechanism shown out nice and neatly and prettily. We could, yes, it's a word. We can also do it, believe it or not, with aromatic rings. Second semester chemistry, not a big a deal to worry about this semester. Would we expect that to happen? No, because the aromatic ring is super, super stable, which is one of the reasons why the reduction carries the person's name. It's typically referred to as a Birch reduction when you're looking at the aromatic ring. Oxygen, substitution and elimination. Okay. Oxygen is synthetically useful due to its lone pairs, making it a nucleophile and a base. Okay. Because it is electronegative, what does that mean? It pulls electrons towards it really well, making what about our structure? It makes our carbon, say, partially positive, making it a electrophile. Or it pulls the electrons away from the hydrogen, making the structure an acid. So alcohols are very synthetically useful. Almost all routes of mechanisms tend to go through alcohols because they have all these possibilities. But for that same reason, they are now very, very painful reagents to work with. Because I take that single functional group, and instead of going one direction, I have 4 different directions I can go. That means I want to limit that chemistry, and we'll try to come up with ways to change the alcohol functionality into other functional groups, like alkyl halides on the far left. We've seen this, where we could come up with ways on how that could possibly work. HCl, HI, HBr. We'll look at the roles of, say, zinc chloride in second semester, but you should be able to do all 3 of those already. Okay? The alcohol can act as a base, picks up the hydrogen, making water a great leaving group. If it leaves the structure, then what do we need? The bromide, iodide, or chloride can then come in and replace it, and we have this alkyl halide substitution, our alcohol substitution. Okay? We could go through and add dilute sulfuric acid. Dilute sulfuric acid ends up with this weird, goofy-looking structure. If we go through and make it concentrated, though, we can do the full elimination, which we've seen. What's happening under dilute conditions? Anything look familiar in there? I tried to draw it so that it was less confusing. Sulfuric acid is acidic, so we could protonate that alcohol, make it a good leaving group. Say we form a carbocation, what would we need to stabilize that carbocation? A negative. But sulfate can't act as a negative. There's no other nucleophile floating around. But remember, under dilute conditions, not all of the alcohol is converted across into the good leaving group. Some of it is still OH, which means some of it is still, begins with an N, still a nucleophile. And we can get 2 molecules of our alcohol reacting with each other. Okay? So it's recognizing the chemistry that you already have available to you and processing your way through. I don't know why I decided to keep this slide in here, because you're not responsible for these reagents yet. Okay? But they're good other activations. Why might these be a little bit better than, say, these? What do you not notice here that you do notice here? Stereochemistry. When we look here, stereochemistry is clearly marked. Whereas here, it's not. Why? Mix of products, single product. Okay? These reagents tend to be better because they are very specific to those particular products. Okay? And with that, we'll have to go ahead and end because I already talked too much.